so interested in the newt?
The newt can regenerate various different types of tissue very efficiently. We are trying to understand these mechanisms and then to make use of them in mammals and in humans.
The newt's special skills even protect it during a heart attack. Scientists can use magnetic resonance imaging, MRI, to observe how the newt's heart recovers. During a heart attack, part of the heart is no longer properly supplied with blood. The cells of the heart muscle do not receive enough oxygen. Scar tissue is formed and cannot contract in the same way as a muscle. But in the newt, the scar tissue is turned back into functioning muscle cells again. The MRI shows that just a few weeks after the heart attack, the newt's heart is beating at full strength again. Thomas Braun and his staff want to know why newts can do this, but humans can't.
In humans, once a scar has formed in the heart muscle, we initially have a very static situation and nothing changes. The newt is more dynamic. It repairs these defects, absorbs the scars, and can regenerate tissue that is fully functional. There's no doubt that this is a fascinating subject.
In some cells of a damaged newt heart, we can recognize condensed chromosomes, meaning that these cells are dividing. Only immature cells can do this. Clearly then, specialized heart cells develop back into immature cells. They de-differentiate. And later, they develop back into striated heart muscle cells again. We can imagine it like this. These are stem cells. They're the babies among the cells. They can develop into virtually all types of cell with different functions in the body. For example, as immune cells, they can fight off germs. As nerve cells, they can process information. Or as heart muscle cells, they can pump blood through the body. On its way from a baby cell to an adult cell, the cell goes through an intermediate state. It's young and largely undifferentiated. With training and time, it will mature, and it will become a powerful heart muscle cell. Then it will need a lot of oxygen, but that is what is lacking during a heart attack. In humans, this is what causes the heart cells to die. The newt's trick is that it can rejuvenate its heart muscle cells. To do this, the cell will have to undo virtually everything that happened during the ripening process. The cell dismantles its supporting skeleton and all the elements which allowed it to beat, and it stops working. It's now a de-differentiated precursor cell. They need less oxygen than mature heart muscle cells, and can therefore survive better if there is a shortage of oxygen.
As an American colleague once said, rewinding, winding back a program, so that cells are put into the situation of reacting in the same way as young embryonic cells.
Could this trick also work for humans? And if so, can scientists wind back the cell program? And indeed, the scientists discovered, in humans too, after a heart attack, mature heart muscle cells are rejuvenated and become youthful precursor cells. However, far too few muscle cells become precursor cells again. There are not enough to carry out the repair. So scientists want to know whether it is also possible for humans to transform more muscle cells into precursor cells, so that they can avoid being suffocated. They're examining how the heart regenerates in mice. Like the newt, newborn mice can completely reconstruct their hearts. Older creatures, however, can no longer do that because the heart muscle cells can only de-differentiate during the first week of life. Scientists think that newborn mice possess a signal substance for this de-differentiation, which they no longer have later when they're older. They want to find this signal substance.
We are certainly in a position to carry out tests of that kind with hundreds or even thousands of different substances, which we add to isolated cells, and then analyze the effects